Hi everyone, this is our second video of Beee. In our previous video, we have gone through uh, network elements, that is network, circuit, and then coming to the examples of this network element, that is a resistor, inductor, and then capacitor. Actually, I thought to discuss a few points in the previous session, but unfortunately, I've forgotten to discuss about it. And now coming to this inductor, here I wanted to discuss this graph, which is a graph between this flux and the current. It is a sinusoidal wave, and this is your positive, that is magnetic flux, which is positive, and here at the bottom this is the magnetic flux, which is negative. And the difference between this inductor and capacitor is only one, that is, in inductor the magnetic field is involved, but while coming to this capacitor, electric field is involved, and the role of current is done by capacitance in this capacitor. And also I wanted to discuss this point, that is, your inductance and capacitance are called as duality of each other, since they both possess similar properties, like energy is stored in both of the cases, right? So this inductance and capacitance are called as duality of each other. And now in this video we are going to learn about Kirchhoff laws, that is KVL, and in my next coming video we'll go through KCL. And now firstly coming to this KVL, which is nothing but your Kirchhoff's voltage law. Here in simple word to say, your voltage rise, that is, in any closed loop your voltage rise should be equal to your voltage drop, or else sum of algebraic currents across any closed loop must be equal to, that is your voltage differences must be equal to 0. Now let us go through this in detail. See, firstly here you have to remember a sign convention, which is very simple. See, as you go from positive to negative, since if you move from positive to negative, then you have to take that as negative, and if you move from negative to positive, then you have to consider the sign convention to be positive. And the important key point to remember is your current always flows from positive to negative, that is, your conventional current always flows from higher potential to the lower potential, and whenever the current enters, it is considered as the positive potential, and whenever the current leaves, it is considered to be negative potential. Okay, and now let us go through this series circuit. See, this is your circuit. Now here if you see this, firstly, whenever you solve a problem of KVL, just mention the name of a loop so that it may be easier to identify. So let us suppose these as A, B, C, D, okay, and this loop is said to be A, B, C, D, A, okay. And now coming to here, let us suppose the direction of current is in such way. So as previously here we have discussed, the current always moves from positive to negative. See, since your current is moving in this direction, so it is moving from positive to negative. If your current direction is in this way, then also it is moving from this positive to negative. Okay, remember this point. And now coming to here you have a resistor involved, R1, R2, and then R3. And now applying KVL to this loop, as we know that the sum of these voltage differences, right, sum of these voltages should be equal to 0. Okay, now let us suppose we are moving from here, as since we are moving from positive to negative, and here you know that V is equal to IR, right? So since we are moving from positive to negative, your sign convention will be negative. And as we know that V is equal to IR, across this R1 resistor, your voltage will be, the current flowing through this R1 is I, right? So IR1, but since it is moving from positive to negative, it is minus IR1. And now coming to this BC, here you have a resistor R2. And since again your current direction is in this way, see your current is in this way, right? So as your current moves from positive to negative, as you are going from positive to negative, it is again negative, right, according to the sign convention. And the voltage across these resistor is current multiplied by the respective resistance, right? So it is minus IR2. And since we move from C to D, here you have a resistor R3, and again we know that it is moving from positive to negative. So according to sign convention, it is negative again, as the same current I is flowing throughout the circuit, minus IR3. And since here, see, whenever this is your positive terminal and the short one is your negative terminal, and as here we are moving from negative to positive, it should be positive. So according to our sign convention, it is positive. So plus V, this should be equal to 0. That is what KVL, right? The sum of the that is voltage across this closed loop should be equal to 0. And now if you write this, we can write this in this way, right? That is minus IR1 minus IR2 minus IR3 is equal to minus V. And if you take minus as common, here you will get IR1 plus IR2 plus IR3 which is equal to minus V, and this minus get cancelled, and then we'll get V is equal to I into R1 plus R2 plus R3. And if you observe this circuit, here your R1 plus R2 plus R3 is nothing but your effective resistance. Since these were in series, we consider the effective resistance to be R1 plus R2 plus R3, right? So here your V is nothing but I into R effective. Now your I into R effective, V is nothing but I into R effective, which is equal to I into R1 plus R2 plus R3. And here this I and I get cancelled. By this you get R effective is equal to R1 plus R2 plus R3, which is in series. And in a simple way to define this KVL, in any closed loop, this voltage rise should be equal to your voltage drop. And in series we know that the current remains same, right? And the voltage only gets divides, that is voltage is divided in series. And we'll discuss about KCL in the next video. Okay, or else we'll also continue KCL in this video itself. So here KCL, which is nothing but your Kirchhoff's current law. Here you have this circuit, right? This KCL is nothing but your sum of currents meeting at a junction or node is 0. Now you may get a doubt, what is this junction or node refers to? A junction or node is nothing but whenever you have 3 or more elements involved, that will be considered as junction. So to consider a junction or node in a circuit, it must be involvement of more than 2 elements, that is at least 3 elements should be involved in order to consider that particular node or junction. Okay, and here these resistors are in parallel, right? And let us suppose this as a junction. Since here R1, R2 and the V, that means 3 elements are involved, right? So let us consider this as a junction. And now coming to here, whenever you have a junction, there will be a current division. Let us suppose, we can assume this current direction as of our wish. So let us suppose this as I, and this current as I1 and this current as I2. Okay, and always remember that the same I2 current flows here. See, here I2 is in this case, and whenever you come to here, it will be in opposite direction, and here your I is in this direction, right? So whenever you come to here, your I will be opposite direction to that of this. So now the sum of currents meeting at a junction or node is 0. This is nothing but your KCL. And the currents which are towards the junction is considered to be positive, and the currents which are away from the junction is said to be negative. Now I'll conclude this sign convention in a easy way. Let us suppose this junction A, and let us suppose this is a current I, this is I1 and this is I2. Now in this junction A, your I current is towards the junction, right? That means it is heading towards A. It means you should consider this I to be positive. And now if you see I1, it is away from the junction, right? That is, it is moving away from this A. So it should be considered as negative. So I minus I1, and since your I2 is also moving away from this junction, right, so it should be considered again as negative. So I minus I1 minus I2, which is equal to 0, which is nothing but I is equal to I1 plus I2, or simply the sum of currents entering the junction is equal to sum of currents leaving the junction. Now the sum of current entering the junction is only I, and leaving the junction is I1 and I2. And now applying KCL at this junction A, see at this junction A, the sum of current, the current which is entering is I, and the current which is leaving are I1 and I2. That means I is equal to I1 plus I2, right? So your I is equal to I1 plus I2, and since we know this relation V is equal to IR, we can write I as V by R. So this I1 will be V by R1 and this I2 will be V by R2, and this I is nothing but V by R effective, that is the total effective resistance, right? And if you take V as common here, it will be your 1 by R1 plus 1 by R2, and by taking this LCM we'll get R1 plus R2 by R1 R2, and now this V get cancelled, and 1 by R effective, which is nothing but R1 plus R2 by R1 R2, and now your R effective will be R1 R2 by R1 plus R2, which is in parallel, right? And in such a way you calculate you'll solve this KCL problems and the KVL problem, and this is one of the important point to note, that is whenever you take a circuit in which the resistors are connected in parallel, your R effective will be lesser than the least resistance connected in parallel always. To get more clarity regarding this, let us go through an example. Let us suppose R1 is equal to 2 ohm and R2 is equal to 1 ohm. Okay, now your R effective is equal to, according to this formula, R1 into R2 by R1 plus R2, right? So it is nothing but 2 by 3, which is nothing but 3 divided by 2 means 0.66. Okay, 0.66 is nothing but which is lesser than this R1 and R2, right? That is your R effective will be lesser than the least resistance connected in parallel always. Hope you have understood these KVL and KCL, and in next video we will go through few problems, and if you have any doubts regarding this topic, feel free to ask me. Definitely I'll respond to each of your comments, and let me know whether to continue this series or not. Don't like to share, subscribe my channel only if you like the content. Thank you for watching.